everybody. Today I'm going to be talking about ancient climate change. My partner and I split up climate change into like the ancient side and then the more recent human-caused description of climate change. So I'm focusing on the ancient stuff and kind of just some basic ideas behind climate and climate change. So first thing is the difference between weather and climate. So most of y'all are familiar with this. Weather is short period atmospheric conditions. So that's where you look at the weather and it's going to be sunny and 60 on Saturday. Versus climate, which is a long period of time. So those are for a specific region. What are the regional average temperatures or precipitation, atmospheric behavior over a long period of time? So that's where you can say, look back at many years of data and say that on average, let's say for this graph down here, it looks like it's 60 in May. And that's based off of many, many years. So when talking about Earth's climate, we need to think about where Earth is getting its energy, and that's from the sun. And for the most part, the solar radiation that is in contact with Earth is pretty steady. There are some fluctuations, but overall, we get a pretty steady amount of solar radiation. And only about 48% of it actually makes it through our atmosphere and to the surface of Earth. 23% of that solar radiation is absorbed by the upper atmosphere, and 29% is just reflected. And then when that 48% of solar radiation does make it to the surface of the Earth, here we've got a breakdown of 25% is evaporated, 5% is lost through convection, and then 17% is re-radiated as radiation. The radiation that's coming in is ultraviolet, so that UV radiation is what you wear sunscreen to protect yourself from. But then what's re-emitted is longer wavelength, so it's more going to be infrared radiation that is re-radiated from the Earth. So factors that can affect the energy budget, so the amount of energy that's either trapped here on Earth or bounces off. One of the big things that we're going to talk about more is greenhouse gases. So greenhouse gases trap the re-emitted infrared radiation in our atmosphere. So these gases allow the ultraviolet radiation to pass through, but then when that infrared radiation is re-emitted from the surface, it gets trapped by these different gases. We'll talk about more in a minute. Either the melting or freezing of ice caps has a big effect on our energy budget, what's happening with energy. So when our ice caps are larger, we've got more of a bright, kind of shiny, reflective surface for radiation to reflect off of. And here I say that they affect the albedo, which is the reflectiveness. So when we have larger ice caps, there's a higher albedo for the Earth, and more radiation is reflected off versus when the ice caps melt and they're smaller, more of that radiation hits things like water or land, and it's absorbed more than it would be off of ice. And then aerosols, so dust particles in the atmosphere that could be from volcanic explosions or some sort of big explosion, like a bomb, can emit a lot of dust that can be suspended in the atmosphere. And when there's a lot of dust in the atmosphere, that actually reflects more radiation because, let me just go back a minute here. So that radiation that's coming in and is reflected off of the atmosphere, it can increase that percentage. So potentially a really, really big volcanic eruption could temporarily cool our atmosphere, cool the surface. So we'll talk a little bit about the greenhouse effect. Y'all should be familiar with this just from I don't know, being alive. But here's a breakdown of the composition of our atmosphere. So our atmosphere is mostly nitrogen, almost 21% oxygen, a little bit of argon, and only less than half a percent carbon dioxide, and then some other trace gases down here. But that carbon dioxide turns out to play a really big role in the greenhouse effect. So greenhouse gases are a primary indicator of a warm period of climate because they trap that excess radiation in our atmosphere. The main greenhouse gases are water vapor, methane, nitrous oxide, and then carbon dioxide. Carbon dioxide is considered the primary greenhouse gas, and that's particularly because it stays in the atmosphere for a really, really long time. Um, and since it does have a larger percentage compared to these other gases, that's the one we kind of focus on more. Right, so quick breakdown of the carbon cycle. So really we're worried about when there's excess carbon dioxide in the atmosphere, and that's caused when there's an imbalance in the carbon cycle. So some ways that carbon can end up in the atmosphere is through things like volcanic eruptions, human emissions, but I'm kind of focusing more on the ancient stuff, respiration from animals and trees, and then there's exchange between the atmosphere and the ocean. So carbon dioxide can be dissolved in the ocean. It's also ends up in ocean sediments. And when marine life shells contain a lot of carbon, those can end up as ocean sediment and ends up kind of in our rock cycle. Fossil carbon, so that's your coals and your petroleums. Those are organic materials that have been underground for a long time. So there's a bunch of different ways that carbon moves throughout our world, but it's just when there's an imbalance that we end up with more carbon in the atmosphere and typically warmer climates. So I'm going to talk a little bit about past glaciations or ice ages. So this is kind of a maybe overwhelming diagram here, but what it's showing is almost 4,600 million years ago, different ages here, and these blue boxes represent ice ages or glaciations, glacial periods. So in the last 540 million years, we've had multiple glacial periods, and we know that there's one about 250 million years ago, but before that, it's kind of harder to get into those really, really far away periods, just to have evidence to support them. But we do have evidence to support at least back to the Huronian glacial period. All right, so how do we know that these periods existed? These were times where there was a lot of glaciers and the general climate was a lot colder. And so the times between these glacial periods are a lot warmer. So there have been fluctuations in our climate over and over again through the past. So let me move that. So to figure out when past glacial periods were, we use these things called proxy indicators. So a proxy indicator is a biological, chemical, or physical signature preserved in the rock, sediment, or ice record that acts like a fingerprint. So for our evidence of really, really old glacial periods, we need to study the rock record. So it's a study of rock formations to look for glacial sediment, which is evidence that there was a glacier in that area some time ago. So one example of that is at the Mineral Fork Formation in Utah. That gave us evidence for Um, I actually forget. I think it was a hero. I'll get back to you on that. Sorry about that. But it gave us evidence for some of the glacial periods um, a really long time in the past, older than 65 million years, because that's um, how far we can look into the past with sediment cores. So sediment cores go back as far as 65 million years, and that's where you're going to an area deep in the deep sea and drilling down and grabbing columns of sediment that give us records for the sediment really really long time in the past. Um, in these sediment columns, we can find evidence of fossils, so little microfossils. That gives us information about the climate because different types of microorganisms prefer different climates. So if you find a diatom in an area that maybe later you have a different type of fossil, that'll give you information about the type of climate. And then looking at the oxygen isotopes in different layers. So comparing oxygen 16 to oxygen 18. Oxygen 16 is lighter and evaporates easier. So if you have we know that 40 million years ago there was more oxygen 18 compared to another time period. It means that more oxygen 16 had evaporated from the ocean. Potentially it was a period of warmer temperature with more evaporation, and so it left more oxygen 18. All right, and then we can also look at ice cores. Ice cores don't go quite as far back as the sediment cores. They go, so far we've gotten 800,000 years in the past, so we can drill down into the ice caps and find ice that's 800,000 years old, which is pretty incredible. Again, they're looking at oxygen isotopes. They can see that ratio gives us information about the climate, and we can actually look at what the atmospheric composition was for years up to 800,000 years ago. So they can essentially take a slice of this ice core and dissolve it and capture the gas and analyze the gas to see what sort of composition existed at that time. And kind of leading into what my partner for this curriculum development is going to talk about, carbon dioxide in the past 800,000 years has ranged from 170 to 300 parts per million up until recently, and it's now over 400 parts per million since humans have been around, adding more carbon dioxide to our climate. Awesome. Thanks a lot, y'all.